The topic of this video is Chapter 4, Direct Proof. In this chapter, we will prove statements of the form, if P is true, then Q is true. P is our hypothesis and Q is our desired conclusion. Our general strategy will be to assume that P is true. We'll then give a step-by-step logical argument using definitions, mathematical facts, basic algebra, and previously proven results. The conclusion of this argument should be that Q is true. A few notes about proofs. Proofs should be written in complete sentences. These can be regular English sentences or mathematical sentences using logical symbols that we've used so far in this course. Never write a statement that is not already shown to be true, aside from stating the hypothesis. The format of this might be assume that the hypothesis is true or suppose that P is true. A proof should be unambiguously clear to anyone who has the prerequisite knowledge. So the proofs that you write in this course should be, at each step, absolutely clear and unambiguous to anyone else taking this course. The first few theorems we prove will require the following definitions. First, an integer n is even if n is equal to 2k for some integer k. So for example, the integer negative 28 is even because negative 28 is equal to 2 times negative 14, and negative 14 is an integer. 0 is also an even number because 0 is equal to 2 times 0, and 0 is an integer. An integer n is odd if n is equal to 2k plus 1 for some integer k. So for example, 13 is odd because 13 is equal to 2 times 6 plus 1, where 6 is an integer. And negative 3 is odd because negative 3 is equal to 2 times negative 2 plus 1, where negative 2 is an integer. So we're going to start by proving a pretty basic statement. We are going to show that if n is an even integer, then n plus 1 is odd. So we're going to begin our proof by saying, suppose n is even. So we have explicitly stated that the hypothesis P is true. Now we're going to break apart the definition of what it means for the hypothesis to be true, in this case that n is even. Then n is equal to 2k for some integer k. And we could write that out in sentences, or we could write it using the symbolic logic that we've previously used. Now let's look at the conclusion we're trying to draw. We're trying to show that n plus 1 is odd. So n plus 1 is equal to, n is 2k plus 1, where k is an integer. And great, we have shown that n plus 1 is equal to 2k plus 1. So therefore, by definition, n plus 1 is odd. And we have finished our proof. There are various ways that we could show that. One is to write a little square, either with nothing in it or with a little scribble inside. Another way is to write QED. This is Latin for that which has been demonstrated. Or we could write W to the fifth, which was what we wanted. So now I'd like you to try the following. So I'd like you to prove that if n is odd, then n plus 1 is even. So I'd like you to actually pause, get out a piece of paper, and try on paper. So actually try to write out a proof for this. It's obviously going to be fairly similar, but there is one additional step that was not in the previous proof. Okay, so hopefully you've given that a try. Let's see what it might look like. So we first want to assume the hypothesis is true. We could do that by saying, suppose that n is odd. Then, by definition, n is equal to 2k plus 1 for some integer k. And we could write by definition if we wished. Okay, so n is equal to 2k plus 1. We're trying to prove something about n plus 1. So we could say something like, observe that n plus 1 is then equal to, well, n is 2k plus 1, and we could simplify that, so that's equal to 2k plus 2. And what are we trying to prove? We're trying to show that, n plus 1 is even. We're trying to show that n plus 1 is equal to 2, say j, for some integer j. What do we know at this point? Well, we could factor a 2 out of that expression, and so this would be equal to 2 times k plus 1, where k plus 1 is an integer. And therefore, we have shown that n plus 1 is in fact even. So, by definition, n plus 1 is even. And we have completed that proof, and there we go. So there are many ways in which your proof might have varied from this proof. So some of the connecting words, for example, that I used in this proof were slightly different than the connecting words or connecting phrases I used in the previous proof. We could have used symbolic logic, or we could have written certain statements out in words. And so there is a lot of variety in how a proof is approached, or a writing style for proofs, just like in writing style for any kind of writing. Okay, so let's do another one together. Here we want to prove the proposition, if a is an odd integer, then a squared plus a plus 1 is odd. By the way, we use the term theorem and we use the term proposition. A theorem is a major statement that is proven. A proposition could be a smaller theorem, something that's a little bit less important or less grand. So this might be a good example of a proposition. So we want to show that if a is an odd integer, then a squared plus a is plus 1 is odd. So again, we're going to start by assuming the hypothesis is true. So we could write, assume that a is odd. If a is odd, then by definition, a is equal to, we could switch it up at this point. Let's say a is equal to 2m plus 1. The names that we give to our variables doesn't matter. And so we could observe that a squared plus a plus 1 is then equal to 2m plus 1 squared plus 2m plus 1 plus 1. So we're sticking in 2m plus 1 anywhere that we see in a. We can now simplify this expression. So 2m plus 1 squared, that's 2m plus 1 times 2m plus 1 plus 2m plus 1 plus 1, so 2m plus 2. This is 2m plus 1 multiplied by itself. So first term's 4m squared plus 2m plus 2m plus 1 plus 2m plus 2. And then we've got 4m squared plus 6m, when we combine like terms, plus 3. We're trying to show that a squared plus a plus 1 is odd. So just in the background, we could say to ourselves, okay, we want to show that a squared plus a plus 1 is equal to 2j plus 1 for some j in the integers. So that's what we're trying to show, and we could put that on our scratch paper, but it shouldn't be part of our proof. So we want to have 1 by itself. So 1 plus, now can we factor a 2 out of the remainder? So we'd have 2 times 2m squared plus 3m plus, this was 3, we took one of them away, we have 2 remaining, so there's 1 times 2 left, where 2m squared plus 3m plus 1 is an integer. And so, by definition, a squared plus a plus 1 is odd. So we've finished that proof. Okay, so let's do one more proof in this video. Let's suppose that x and y are odd integers. We want to show then that x plus y plus 5 is odd. And at this point, I'd encourage you to try it as well. So give this one a try before we look at it together. And in general, I'd really encourage you, when you're doing these proofs, especially in the beginning, to use scratch paper. And if something can be rewritten more elegantly, so do that. So be really willing to rewrite your proof. And your proof should not contain any extra material. So up above, when we did our little scratch work on the side, again, that should not be part of our proof. It can be part of the scratch paper on the side, but it should not be within the body of our proof. Okay, let's see how those turned out. So suppose x and y are integers, then x plus y plus 5 is odd. We should start out by assuming the hypothesis is true. So suppose that x and y are odd integers. We then want to expand what that means by definition. So x is equal to 2k plus 1 for some k in the integers, and y, well, what can we put here? Can we write y is equal to 2k plus 1 for some k in the integers? At this point, this would be an error. We would be assuming more than what was given by the hypothesis. So x and y are odd integers. Here, 2k plus 1 and 2k plus 1 are odd, but assuming this as well makes the assumption that assumes that x is actually equal to y, not just that they're two odd integers, but that they would be two odd integers that are equal to one another. So we need to assume that y is equal to 2 times some new variable, like j plus 1, where j is an element of the integers. So we were trying to prove that x plus y plus 5 is odd. So we could now observe that x plus y plus 5 is then equal to, with substitution, 2k plus 1 plus 2j plus 1 plus 5. We're trying to prove that this is odd, so we really want one of the plus 1s by itself. So this is 2k plus 2j plus 1 plus 5 plus 1, so plus 6 plus 1 by itself. And then this is equal to, we want to show that this is equal to 2 times some integer plus 1 to show that it is odd. So 2 times k plus j plus 3 plus 1, where k plus j plus 3 is an integer. And therefore, x plus y plus 5 is odd, and we have completed our proof.